Japan is building its next bullet train, but this one is different. It is designed to move at 500 kilometers per hour, not by rolling on steel rails, but by floating above a magnetic guideway. This is the Chuo Shinkansen, Japan's next-generation maglev line, and on paper, the promise is breathtaking. From Tokyo's Shinagawa station to Nagoya in about 40 minutes. From Shinagawa to Osaka in about 67 minutes. A journey between major regions compressed into the time of a city commute. But the hardest part is not making the train fast. The hardest part is building the world around it. Deep tunnels beneath cities, mountain passages through the southern Alps, massive underground stations, magnetic guideways, emergency access shafts, power systems, water protection, environmental monitoring, rising cost, and a schedule already pushed beyond its original target. Speed is what people see. Construction is what decides whether that speed can ever happen. Japan is not just building another bullet train. It is trying to build a 500-kilometer-per-hour transportation artery through the ground beneath one of the most complex countries on Earth. This is why Japan's next bullet train is so hard to build. For decades, Japan has been known as the country that changed high-speed rail. The Shinkansen became a symbol of speed, precision, safety, and national engineering confidence. It connected cities. It reshaped business travel. It made long-distance rail feel smooth, predictable, and almost effortless. But the Chuo Shinkansen is not simply the next version of the same idea. It is not just a faster Shinkansen on better rails. It is a different kind of railway, a superconducting maglev system. A conventional train depends on contact. Steel wheels touch steel rails. That contact guides the vehicle, supports its weight, and transfers force. But contact also creates limits. At very high speed, friction, noise, vibration, wear, and stability become major engineering problems. Superconducting magnets on the train interact with coils built into the guideway. At high speed, magnetic force lifts the vehicle above the guideway by roughly 10 centimeters. The train is guided, propelled, and stabilized by the magnetic system around it. That small gap changes everything. Because when the train no longer runs like a conventional railway, the railway itself can no longer be conventional. The track becomes a guideway. The guideway becomes an electrical and magnetic machine. The line becomes a precision corridor. And every part of that corridor, geometry, power, tunnel shape, safety, air pressure, emergency access, and maintenance, must work together. A normal railway needs rails. This one needs a machine built into the ground. That is the first reason the project is so difficult. Japan is not only building a train, it is building the system that allows the train to exist. The Chuo Shinkansen is planned to connect Shinagawa in Tokyo with Nagoya first, and eventually extend toward Osaka. The Shinagawa to Nagoya section is about 286 kilometers long. When complete, it is designed to reduce the fastest trip from Shinagawa to Nagoya to about 40 minutes. Eventually, the fastest trip from Shinagawa to Osaka is planned to take about 67 minutes. But the goal is not only speed. JR Central describes the Chuo Shinkansen as a way to create a second major artery for Japan's most important transportation corridor. Today, the Tokaido Shinkansen carries the Pacific side route between Tokyo, Nagoya, and Osaka. It is one of Japan's most important transport lines. It supports business, tourism, commuting, and the movement of people between the country's largest metropolitan regions. But the Tokaido Shinkansen has been operating for more than 60 years. And Japan must always plan for earthquakes, aging infrastructure, and large-scale disasters. So, the Chuo Shinkansen is also about redundancy. A second high-speed spine, a backup for the national corridor, a way to make Japan's most important economic axis harder to break. Japan is not building this because the current Shinkansen failed. It is building it because the corridor is too important to depend on only one main artery. That is what makes this project larger than transportation. It is not just a new railway. It is a national infrastructure strategy. But a strategy on paper still has to be built in the real world. And the real world is where the difficulty begins. Before a maglev train can ever float, engineers must first carve the path it will float through. They must survey the ground, secure land, build access sites, open vertical shafts, launch shield machines beneath cities, excavate tunnels through mountains, stabilize rock, install tunnel linings, build underground stations, place magnetic guideway systems, connect power infrastructure, test coils, validate emergency systems, monitor water, and only then can the train become more than a prototype. The Chuo Shinkansen is not a single construction job. It is a chain of construction battles, and the first major battle is underground. In dense urban areas, there is no empty surface corridor waiting for a new railway. Tokyo is already built. Nagoya is already built. Roads, railways, rivers, utilities, building foundations, subway lines, and underground structures already occupy the space. So the railway has to go below. In urban sections, JR Central uses shield tunneling. A large cylindrical shield machine is lowered into a vertical shaft. At the front, a cutting wheel rotates through soil. Behind it, tunnel segments are installed, forming the permanent lining as the machine moves forward. Above the tunnel, the city continues to function. Traffic moves, buildings stand, people go to work. But deep below, a new railway corridor is being carved through the ground. The challenge is not simply digging. It is digging while controlling settlement, groundwater, vibration, noise, safety, logistics, and emergency access. Vertical shafts are critical. They allow the shield machine to be assembled underground. They serve as construction bases, and later, they can become emergency access points. That means a shaft is not just a hole in the ground. It is the connection between the city above and the high-speed railway below. In the city, the most difficult parts of the project may be invisible, but invisibility does not mean simplicity. It means the difficulty is hidden under everyday life. Every underground station, every shaft, every tunnel segment, every power cable, and every safety system has to fit into a city that was never originally designed around a 500 km/h Maglev line. And once the route leaves the city, the problem changes completely, because then the project faces the mountains. The Southern Alps are one of the defining engineering battles of the Chuo Shinkansen. Here, the obstacle is no longer urban density. It is depth, rock, water, pressure, geology, and uncertainty. JR Central describes the Southern Alps Tunnel as one of Japan's largest tunnels in both length and depth. It is about 16 miles long, with overburden reaching up to about 4,593 feet from the surface. That means parts of the tunnel sit beneath an enormous mass of mountain. At that depth, the mountain is not passive. It pushes, it cracks, it stores water, it changes from one geological zone to another, and every unknown ahead of the tunnel face can become a construction risk. In mountainous areas, the project uses the new Austrian tunneling method, or NATM. This method does not treat the surrounding rock as something separate from the tunnel. It turns the rock mass into part of the support system. After excavation, workers spray concrete onto the exposed surface. Rock bolts reinforce the surrounding ground. Concrete, bolts, lining, and mountain rock work together to stabilize the opening. The method is flexible, which matters in mountains where geology can change suddenly, but flexibility does not make the work easy. Every step forward requires judgment. What kind of rock is ahead? How much water is moving through it? How much support is needed? Can the ground stabilize itself? Or does the tunnel need heavier reinforcement? To reduce uncertainty, JR Central uses pilot tunnels and ultra-long boring surveys. A pilot tunnel can investigate geology and water conditions before the main tunnel advances. Ultra-long boring can examine ground far ahead of the tunnel face. This matters because in a deep mountain tunnel, a surprise is not just a delay. It can change the construction method. It can increase cost. It can affect safety. It can change the schedule. And it can raise new environmental questions. That is why the Southern Alps section became one of the most important parts of the entire project. Not because it is simply a tunnel, but because it concentrates so many risks in one place. Deep geology, high overburden, groundwater, environmental sensitivity, and the need to build a tunnel precise enough for a railway that will eventually carry passengers at extraordinary speed. But the deepest problem in the mountains was not only the rock, it was the water moving through it. That is where Shizuoka became central to the story. The Shizuoka section became a major delay issue because the tunnel connects engineering with water resources, the Oi River Basin, and the natural environment of the Southern Alps. For tunnel engineers, water may look like a construction condition. Water enters the tunnel. It must be measured, controlled, treated, diverted, or returned. But for communities downstream, water is not an engineering variable. It is agriculture. It is industry. It is ecosystems. It is daily life. It is trust. That is why the Shizuoka issue cannot be reduced to a simple story of one prefecture blocking a train. The real story is more difficult. When a tunnel passes through a mountain, it can interact with groundwater. If water flows into the tunnel, local communities want to know what happens beyond the construction site. Will river flow change? How will groundwater be monitored? How will tunnel water be handled? What happens if predictions are wrong? Who is responsible? What data will be shared? And how can people trust a project whose most important work takes place underground, out of sight? By 2026, Shizuoka Prefecture said all 28 dialogue items with JR Central had been completed. That was an important milestone, but a completed dialogue is not the same as the end of responsibility. The next stage is implementation, environmental conservation measures, monitoring, risk management, local explanation, and proof that commitments made on paper can survive the conditions of real construction. The deeper the railway goes, the more it has to answer to the land above it. That is what makes the Chuo Shinkansen so difficult. The tunnel is not only a tunnel, it is a negotiation between engineering and environment. A high-speed railway may be designed in drawings, but it must be accepted in the real world. And the real world includes rivers, farms, ecosystems, local governments, experts, and communities that want evidence, not just promises. This is where the schedule problem becomes easier to understand. The original target was to open the Shinagawa to Nagoya section in 2027. That target is no longer possible. JR Central stated that the Shizuoka construction section was directly causing the delay, and that without a prospect of starting tunnel excavation there, a new opening date could not be predicted. In a mega project, delay is not one event. It is a chain reaction. A station can be under construction. A tunnel can be completed somewhere else. A guideway can be installed in another section. But a railway is not useful as disconnected pieces. Until the entire corridor connects, the system cannot operate as intended. That means one unresolved section can affect the entire line. A few kilometers of difficult mountain tunnel can reshape the schedule of a national infrastructure project. And the schedule is not the only pressure. The Shinagawa to Nagoya section alone is estimated at about 7.04 trillion yen. That number is not just the cost of a train, it is the cost of tunnels under cities. Mountain excavation, underground stations, magnetic guideways, power systems, emergency access, safety infrastructure, environmental conservation, monitoring, land acquisition, testing, and time. Every delay affects planning. Every unknown increases risk. Every environmental measure adds responsibility. Every construction decision must still support one final goal: a railway designed to move people safely at 500 kilometers per hour. That is why the train itself can be misleading. On camera, the Maglev looks clean, smooth, almost simple. It floats, it accelerates, it disappears into the distance. But that image hides the enormous construction effort underneath. A 500 km/h railway is not fast because the train is fast alone. It is fast because the entire world around the train has been engineered for speed. The ground, the tunnel, the guideway, the power, the station, the emergency systems, the environmental protections, the monitoring, the permissions, the public trust. All of it must work. All of it must be built, and all of it must be accepted. To understand the scale, look at what has to happen before the first passengers ever board. The ground must be surveyed. Urban shafts must be opened. Shield machines must carve tunnels beneath active cities. Mountain tunnels must advance through uncertain rock. Water must be measured and managed. Tunnel linings must stabilize the corridor. Guideway coils must be installed with extreme precision. Power systems must be connected. Stations must be fitted into dense urban environments. Emergency routes must be tested. Control systems must be validated. And the train must prove that it can operate safely, reliably, and repeatedly, not just on a test line, but as a public transportation system. That is the difference between a technology demonstration and a national railway. The Chuo Shinkansen is not waiting for one magic breakthrough. It is waiting for thousands of construction decisions to line up correctly. And that is why it is so hard, because the future does not fail or succeed only in the laboratory. It succeeds in tunnels, in permits, in mountain rock, in cost controls, in community meetings, in water monitoring, in emergency planning, in years of work that most passengers will never see. If Japan succeeds, the Chuo Shinkansen will not only change travel time, it could change the shape of distance inside Japan. Tokyo, Nagoya, and Osaka could feel closer than ever before. The existing Shinkansen and the new Maglev could create a stronger double network. The country's main corridor could become faster, deeper, and more resilient. And Japan would show that high-speed rail still has another frontier. Not just faster trains, but more integrated infrastructure. But that future is not built by speed alone. It is built by geology, by tunnels, by shafts, by guideways, by power systems, by surveys, by construction workers deep underground, by engineers reading the mountain ahead, by environmental monitoring teams watching rivers and groundwater, by communities asking difficult questions, and by years of patience between ambition and reality. Japan's next bullet train is hard to build because it is not one challenge. It is speed, magnets, cities, mountains, water, cost, schedule, safety, and trust, all combined into a single line. The train may one day float above its guideway, but the project itself is carried by everything hidden beneath it. This is where high-speed rail meets the mountains beneath Japan, and where the future of transportation must first be carved through the earth.